Okay, everyone, welcome back to class, and I hope you're having a good day. Hope everything's going as well as it can be right now, and if it's not going well for you, please reach out for some help. But today we're going to talk about food webs and trophic pyramids, and talk about three key questions. I'm going to try to make this short so you invest as much as the energy you have in doing the activity today. So we're going to talk about how food webs move energy through ecosystems, what controls the size of populations at each trophic level, and really lay out the idea of a trophic level, and then talk about the role of keystone species, and also introduce the idea of a trophic cascade into things today. So let's get started with our lecture. And we'll see if I can keep this under 10 minutes. All right, so first, just wanted you to think about things like this. We're going to start off, if your life had a video game like Life Bar, how many hearts do you have right now, right? And what opportunities do you have to power up? And where is that extra power going to come from, right? And so if we think about the ecological Life Bar, it's the species interactions that move matter and energy through the ecosystems, right? So if you're an animal that wants to keep your Life Bar going, you're going to need to find energy and materials to stay alive from other organisms, or from the sun, right? And one of the ways that that's represented in the flow of energy in an ecosystem is with a food web. And so, they start with all of the energy in the food web starting with some sort of producer. You'll see the phytoplankton in this example here. And then it illustrates the different interactions that move that energy within the ecosystem, right? But one of the things that I think is always important to be careful with food webs, and this is kind of one of the transitions from, what you've learned about a diagram like this over all of your time, probably since the second grade you've been doing food webs. One of the ways that you need to shift your thinking is to understand that it doesn't show the full range of interactions between species, both predator, prey, and consumption kind of things, but then there are also other ways that energy can be transferred. I often don't include decomposers. And there's also a lot of complexity to it, where different life stages can mean that different organisms, different species, play a different role. Salmon, for example, when younger, will eat some of the things on here, but then when older, could be eaten by them. So, or I'm sorry, the other way around, right? Could be eaten by something, but when older could be eaten by them, or could eat them. Let's keep moving. All right, so then the other idea is the trophic pyramid, right? And so in a trophic pyramid, it just shows that most of the energy is at the bottom of the pyramid with the producers, right? And as you move up to the different levels, you lose energy, and that energy is lost as heat. There's about a 10% efficiency as you move up. So what that means is that in this example, a mouse, let me choose the ant. The ant's going to have to eat 10 pounds of plants to make 1 pound of ant, and then that 1 pound of ant will only create a tenth of a pound of frog, right? So there's not very much. They're very efficient. And it's just a way, or inefficient, and these trophic pyramids are just a way to organize some thoughts, and again, aren't hard and fast, right? There are lots of different ways that it's more complex than this. And so one of the really interesting questions in ecology that the rest of the work you'll do today focuses on is which trophic level controls the others? Is it that the presence of plants and the size of the plant community determines how many grasshoppers there are? Or is it the other way around, that the number of spiders determines how many grasshoppers there are, which then determines how large the plant community is? And so these two ideas are represented by the idea of bottom-up control or top-down control, right? And so in bottom-up control, it's whatever physical limits there are to the amount of plants that control the populations of all the other species in the ecosystem. And top down, there's some sort of keystone apex species that controls the community composition. A third hypothesis is that it's all random. And there are so many variables that it's hard to put any sort of pattern to it all. So the work today focuses around this video, and there's an interactive activity. I'll talk more about it at the end, but it's focused on this research of Robert Payne and his starfish throwing. So I'll let him talk more about that. I'm going to keep moving through this, but one of the ideas, there are 3 ideas in this video that you need to make sure that you understand at the end of the activities in the video is that the idea of a trophic cascade, the top-down control, and the keystone species, right? And so in the trophic cascade activity, one of the things that I want to point out is, and this just has some instructions if you want to do some work on paper, but one of the ideas that you'll see in the activity in the video is that positive means that there's some sort of direct relationship. An increase in one population is going to cause an increase in another, and indirect relationships, and these relationships that are negative indirect, right? So an increase in like urchins is going to cause a decrease in kelp, right? And so then if you look across things that don't actually interact with each other, though, can be relationships that are revealed as you think about trophic cascades, right? And so in this you see there's a direct relationship between the otter and the kelp. But again, you're going to learn more about that. I just wanted to expand the definition of keystone species here too, that often we think of keystone species as predators, and one of the things that's an important takeaway is that the presence of keystone predators means a more diverse community. And so Yellowstone and wolves are some really cool research into that if you want to look into that as part of a bioexploration or something. We've also got keystone modifiers, so beavers, that change the ecosystem in a way that allows other species to grow. So all the wetland plants that can live in a beaver swamp wouldn't be there without the beavers. We've also got keystone mutualists that facilitate the plant species pollination and seed dispersal. We've also got keystone hosts, like these cacti. Lots of things live in those cacti, and so they are a key species for having the biological community that you have in the deserts there. And one of the things that I wanted to bring up in this is that research into keystone species is kind of changing the way people are thinking about ecosystems and the way that they operate. And this, you'll read through this, you can see that there are people that are proposing that the null hypothesis be that every community has a keystone species, and it's up to ecologists to prove that that's not true, rather than the other way around. And so it just kind of represents a way that science changes with new information. And so I just think that's an interesting thing to point out. The other thing is that I want to point out is the idea of stable states in ecosystems. So I'm going to actually go here, right? So community stability means that the number of species are constant, the relative abundance of those species is constant, and those species interactions are fixed. And you get a stable community when you have a rich web of interactions between species, feedbacks within your ecosystem, balancing feedback loops, build resilience because of those relationships. And so the general rule is the more diverse a community is, the more stable it is. And a lot of this depends on the frequency and intensity of changes. And so if I go here, there are kind of a couple different ways to think about it. One is that there can be alternative stable states, and something will push the community from one stable state to another. And so in the example, you're going to learn a little bit more about what happened with sea otters versus without sea otters. So the removal of that keystone predator created a second stable ecosystem, and the return of the otter pushed this ecosystem back in the other direction. But we've also got changes in ecosystems that are driven by succession, so progression of species that come in over time, and then disturbance, things that disturb a community, and then when you have that generally stable state, you get a climax community, right? And so succession has been studied for a while, and what we've got here is kind of a beach example of You get sand, bare sand, and then you've got some grasses and things that start to grow, which then give way to shrubs, which then give way to forest. And I'm not going to spend too much time on this because I'm sure you've talked about it somewhere else in your career. But I do want to just shout out Catherine Kiever here. She was one of the scientists that did some of the first research on actually measuring and illustrating this happening. And at a time when it was hard for female scientists, especially natural scientists, to be taken seriously, she did some really important work. And so, as people have tested these ideas of succession, they've found that there are kind of three general things that are true. Species richness increases over time. The early species are fast and hungry. The late species are slow and conservative. So the early species are selected, and the late species are K selected generally. And you can see kind of some of the things there. And then finally, that the species change the environment in a way that facilitates the growth of other species. So you can't get species that will germinate in the shade until you have shade. All right, and then this is just kind of a list of some of those disturbances that can lead to ecosystems change. So now onto the to-do list and talking about what you need to do to kind of complete this. You've got an activity to do, and let me bring that up actually. Your activity is going to be to 3 steps. Pretty straightforward. 1, there's a video to watch. 2, there's a worksheet with some questions. And 3, there's an interactive activity that you should go all the way through. If your technology prevents you from doing any of these, please let me know. I'll give you some sort of alternate assignment. But I hope to hear from you if you're having trouble with it. And just also want to remind you about the quiz that's due on Sunday. And the exam coming up on the 16th. I will publish a study guide, and then I'll end with our feel-good photo gallery. Some of the pets of your classmates here that they submitted. Hopefully put a smile on your face. So I hope you've got some things to smile about. And again, let me know if you want to talk. And don't forget about your bio explorations. Make sure you're getting those done. All right? Have a good day. And yeah, good luck getting this done.